Meme for the day.
So true.
So experience this with picking out colors for the wedding and all kinds of things like that. They look the same to me, yeah. But anyway, this is kind of funny because I'm not just perpetuating sexual stereotypes. There's actually some genetic differences here. So the genes for color detection are on the X chromosome. So women have double that. You know, they have two of those. Okay, and so then they are likely to have a greater discrimination ability to discriminate colors. Also, men more often suffer from color blindness. Yeah, yeah. Uh-huh. Yeah. Yeah, I went to school with a guy who was in Gen Chem with me and he couldn't see the phenolphthalein color. Yeah, like he couldn't tell if he was at endpoint or not. Yeah. And so he was like, I have no idea. Can you tell me when it changes? I was like, stop. Yeah. That's right, exactly. Yeah. And then here's another one. This one's even cooler. Okay, tetrachromacy. So a small percentage of women may have four types of cone cells, allowing them to see millions more colors than the average person. Yeah. So again, if you've got an extra detector, you can see differences that no one else can see, right? And so think of your digital data points. You know, your point is here, and my data point is here, and my data point is here. But if you've got an extra pigment, maybe you see three other data points. And you can tell the difference between things that I can't even see. Like they are exactly the same, but no, you're saying no, they're not. And so when we have these arguments, you know, we're both right. We're saying that I can't detect. We should probably say I can't detect the difference between those instead of declaring those are the same color. So, anyway, that's kind of fun. So let's focus on the project. I went through and I found a bunch of molecules that many have worked well in the past, but this you would choose one from this whole presentation today, or one on your own. But let's talk about the molecules. I had mentioned last time about the Munsell system for coloring, and I'd mentioned some of those color change results from the National Institute of Justice report. And so, you know, here's an example of different reagents that they use in these color spot tests. And like if you have a plant-like material and you think it might be marijuana, and you do this Ducanol-Levine test, you know, and you extract it in ethanol for THC, you get three spots. If you did a thin layer chromatography separation, you'd get three spots from the different cannabinoids, and you'd have purple blue. So where's purple blue? Here. So you'd have one here, and you'd have another purple blue. So you'd have two spots like that, and then one at purple. So where's purple? Right here. So these spots would look like this. And then if it was T, you'd see a green yellow. Very different, right? So, you know, the the um the Munsell color system is useful, okay, and you can just look. I don't even have to know what the 4x4 and the 7/8 and so on. Those are the different, the chroma and the value, but just knowing the different shades, the hues that these produce, we could see that we could tell easily the difference between a green yellow and a purple blue. Okay. Yeah, yeah. These are spot tests. Yeah, yeah. So there's no difference. Yeah, that's true. Yeah. Oh, yeah. Yeah, yeah, yeah. Yeah, and so these would be called a presumptive tests. So they hit this test, it's presumed to be an illicit substance, but then you need to do confirmatory tests like an FTIR, chromatography, a separation, or some kind of mass spec or something like that. So a more instrument based, one that has a better discriminating power, and hopefully one that's digitized and gives you a good report. So anyway, this was just I talked about the Munsell system. I wanted to show it to you. Okay, so we're going to be doing this project, and I want you to choose your molecules wisely for time and accuracy. So whenever we're doing optimizations, floppy molecules take longer. Okay, and so if we've got a lot of things on the outside of the molecule, the dihedral angles are the things that really take a lot of time. So if you have lots of sigma bonds with floppy things on the end, that's going to take longer to optimize. And because there's not much energy in rotating a big group, um, it's getting the perfect angle, like the correct angle, is going to be unlikely. And so if you wanted to match the color in nature and you have a bunch of options as to the angle of this one particular floppy group, you're probably not going to hit the natural, angle that gives you the color that we see. So it's probably going to be a problem with accuracy too if you have a molecule with lots of flexibility. So I would say, just for this project, lean towards the more rigid molecules, and we'll identify today what I'm talking about with certain molecules are more rigid than others. Okay. This paper, there's a couple of papers on Blackboard just for your use on, like for Friday, since we're not having lecture and you're going to be sitting around really bored. You can read through those two papers on color. It's sort of the publication that I've been teaching from in this last week or two. But here's an example of a fine difference in a molecule. So this is phenolphthalein, okay, and the angle of this carboxylic acid group right here. So this dihedral angle right here, when that's 0 degrees, we have a spacing of 504 nanometers in that wavelength transition, and it gives more kind of an orange color. You see 0 degrees here. And if we rotate that 90 degrees, so this dihedral now is 90 degrees, it changes that. The peak shifts towards the red from 504 to 517, and we get a more accurate color to the phenolphthalein. It's not exactly the same, but this is the experimental color of phenolphthalein, which you've seen, that pink color. Yeah. And so this is suggesting that just that rotating of that 90 degrees, that carboxylic acid group. And what is that? That's a carboxylic acid group. That's the pH active group. If you protonate that, then these peaks shift around and now it's colorless. So that peak shifts maybe probably into the UV region. But if you deprotonate it, now that carboxylic acid group can interact with the ring system, change the peaks, move that peak into the visible region, and you get this pink color. Here's an example of peak shape making a difference, and this is taken from the paper. Both of these, notice the names of the paper, beyond lambda max. Because in the past, a lot of times when you're interpreting a visible spectrum, lambda max would be what people would report. So this is lambda max of 550 nanometers. So that's right there in the green region. And so you could say, well, it's absorbing the green. What color would this substance be? Okay, you need more than lambda max. You need the width of that peak, and you need it whether it's asymmetric or not. Because this has the same peak width, but just a different asymmetry parameter. And if that asymmetry parameter was 0.5, the color of this substance would be red. Start out pink and become red. And then if that asymmetry parameter were 2.0, then it tails to the long wavelength side and the color would be blue. So that's pretty crazy if you think about it. Same lambda max, red or blue. I can make a red substance with a lambda max of 550. I can make a blue substance with a lambda max of 550. So this is when I wrote the second paper. I was like, look, we got to do more than lambda max. If we're going to take an experimental spectrum, describe the color, and also report the maximum wavelength, we need to give somebody the width of that peak, and we need to give them the asymmetry of that peak. We should deconvolve it, but not use a Gaussian deconvolution. Use a log normal deconvolution. Fit a log normal to the whole spectrum and give lambda max, give the width, and give the asymmetry parameter. And then people would know how to produce that spectrum again and model the color. So let's learn these 4 families of dyes. This is from my notes in forensic chemistry, where these are the ones that are discussed for these various spot tests. Okay, so triarylmethine dyes. What's the methine? Well, that's this little carbon here that's got only 3 bonds. And we show these as planar, but they're really not planar. They can't be, because these hydrogens would be right on top of each other. So they're banging into each other. So these are twisted slightly, and that disrupts the pi extended pi system and makes it very susceptible to these angles. So the triaromethynes are going to be really tricky to optimize, and so you can do one, but I would say beware, because these twist angles, these angles right here, are going to be hard to optimize. And Gaussian may find a result, but you may get a color that doesn't match the real color of that substance, because it's going to be very sensitive to that angle. Now, if we had time, you could change the angle slightly, redo the modeling of the color, change the angle slightly, model the color, and you could find, okay, in nature, this is probably the angle of these rings. But we don't have time for that. So, but you would know how to do that if that was something that you were doing research on. This azo, this is also a very bad way to draw the azo, because this is a cis, and it's probably trans. Okay, so this whole molecule piece is going to be on this side of that azo linkage. But anyway, the azo dyes, this is the azo linkage right here. Sort of that pi system with the nitrogen atoms. There's a lot of nitro dyes, where you just have nitros stuck onto typically a naphthol or some sort of extended fused ring system. And then the carbonyl dyes, there's not really anything about the carbonyl functional group that makes it colored, but it's when it's connected to an extended pi system. So this extended pi system plus a carbonyl equals color. It just means that the box for that electron cloud is big enough now. Those peaks have moved into the visible region of the spectrum. So let's look at examples of these. So here's some azo dye examples. Azobenzene is the easiest one to do, and it's kind of an orangey red color. Almost looks like Sam Houston orange. And so, but I want everybody to do a different molecule. So when we do our presentations, then it's interesting. So everyone's going to do azulene, a blue molecule, and then pick maybe an azo if you want to do an azo. The only one I would say I don't want you to do is this one, this direct blue one. It's too big. Okay. I don't know, maybe you have a fast computer, but you've got a lot of floppy groups on here. You've got this angle right here too. This one is floppy. And then you've got these methoxy groups here. All of these sulfonate groups. Notice all the sulfonates. SO3s. So, if you were to model that, you might be able to cheat. I don't know, you would have to verify this, but you might be able to cheat and remove the sulfonate groups and just cap it with a chloride or something like that. The sulfonate groups don't add or subtract from the color. They don't talk to the pi system. So they're just out there to provide a charge on the molecule so that it gets sucked into the aqueous phase. And so for water food coloring, if you're going to take a pigment, a dye, something like maybe this aniline yellow, and you want to make a yellow food coloring, then you might stick a SO3 group on there. And now it's going to be in the aqueous phase, and it's going to move into water and make a food coloring. Okay. This one's kind of a combination, this azo violet. So this is also a nitro. So to classify this as a azo dye or a nitro dye, it's both. It's the Venn diagram overlaps on that one. Okay. So these are some options for some of your colored molecules. Here's the carbonyl dye examples. So anthraquinone is the easiest one, but you see how rigid these are going to be. There's really no dihedral angles on these molecules that can flop around. This one over here, I don't know. I mean, maybe that's the structure, but this is a well-known structure. Does anybody know what that functional group is called? Yeah, very good. Amide. And so I think the H would probably be better down here, and then this big R group would be here, right? A trans amide as opposed to the cis amide. Right here, you've got two sterically, interfering hydrogens, and so that's not going to be great. So I would, if I were to make this molecule, I would move this thing over and make the amide trans, yeah, like they typically are in proteins and so on. So. This one is obviously very rigid too. Any of these things that are super planar and so on, these are going to be great to do. Anytime you have dihedral angles, like that one shown, this is one of the worst ones here. This floppy dihedral right here is a problem. Not for our project, okay? We shouldn't do it for this project. But it'd be a great research project, but none of y'all are doing research on the colored molecules. So I don't want your advisor to get mad at me, and take up all your time. Okay. So yeah, carbonyl dyes, those would be great. What makes the carbonyl interesting is it's got those non-bonded electrons. If we were to think of it in a local bonding standing, local bonding mindset, even though we've proven that's not true. Okay, but this non-bonding electrons on the oxygen, you could say yes, oxygen has these extra electrons. We could just agree with that, and that they get plugged into the ring system. So there's ring orbitals up there. Some of the oxygen electrons can be donated to the pi structure, and so that's going to be a big wide box. It's going to be very low in energy, which means it's going to be visible. So what I would do is, if you pick this anthraquinone, right, then take these notes. You can cut this out with the snipping tool, and you can use this as your reference. Okay, so that's the literature value for your color. Okay. So what color is this molecule? There it is. Okay. It's kind of hard to see some of these. This is pretty, I mean, it's violet, but it looks so dark. But I can see it on my screen here. It looks black up there. It looks kind of violet here. So you might try to take that, and maybe you can use the brightening tool, brighten it up or whatever. And again, that might hit one of those when we do the color tool. You might hit one of the lighter colors too. So it's something that you could figure out. You might use the color picker to get the RGB values. In fact, let's do that. Let's for your color, you can get it into PowerPoint or something like that, and then you can make another box, and you do fill, and then you use the little dropper tool. Looks like a little turkey baster, okay? And you go and you suck up some of that color, and it'll fill that box with that color. And then you go to the custom colors, and you'll see the RGB values for that color. You don't have to change them, but it'll populate those three fields when you go to custom color. Then you can read off that color. There may be, you could do image J. You could select that box in image J, do the color histogram. You could get the color that way. So okay. Yes. Yeah, so you might have to get a photograph of the color. If you have the molecule yourself, then you can get a photograph of the color, and then you can use image J to get the RGB values. Yeah, that would be your reference, yeah. The, the what?
Ocean View.
Oh, yeah, the probe. Yeah, yeah. Yeah, for sure. Since you have a molecule that changes color and that's part of your research, yeah, go ahead and use the probe. Yeah, that'd be great. Yeah. She's actually doing experimental work with color. So we have a probe upstairs that will measure the color of it, and so that's pretty neat. We're looking forward to your presentation. We'll let you go last, okay, so that you can show us the whole thing. You'll have a little more time, okay? So she's reserved the last spot. It's kind of like in a car, yeah. Why? It's better than first, right? So here's some aromathine dyes. I've looked all over the internet trying to find examples of these. These are all kind of, they don't not really. Look how strongly colored these. We got oranges and blues and purples and yellows. Yeah, please. And so then, these are very, I don't know, they look kind of boring to me. They're kind of all orangey, pinky, gray. Yeah, so I don't know. And then here's the nitro dyes. These are some small molecules. These are the ones that I've done. Nitroanilines, 2, 3, and 4 nitroanilines. And then here's one that's a 4-methyl 2-nitroaniline. Bright colored orange and yellow. And then this is kind of a brown color. Yeah. So you could do those too. Or you could do some of the natural colorants, but these are kind of big and kind of floppy. So I would sort of steer you away, but this is in the news lately. Have y'all heard about this being in the news? I mean, for the past year, for food, Fruit Loops, and it seems strange that Fruit Loops in Europe use these kinds of pigments, but Fruit Loops in the USA still use all of these, and we're like, well, wait a minute, why would Fruit Loops company make healthy pigments for Europe and not for us? What's going on here? So they've agreed to switch over. Kellogg and all these different companies and Nestle. I don't know the details, but they've decided to switch over to natural colorants. And so we have things like anthocyanins, and strawberries, blueberries, and I don't know what that little blue flower is, but also red cabbage. Have you ever seen red cabbage? If you're ever in the future doing a little demo day or whatever, and you want to do a demo for pH, you don't have to go to the university and abscond with phenolphthalein or anything like that. You can take cabbage leaves, purple cabbage leaves, red cabbage leaves, chop them up, put them in a glass of water, and stick them in the microwave for 30 seconds, and that water will turn deep purple. Okay? That's your pH indicator. You put that in acid, I think it goes one or the other. I forget. I think acid, it goes green, and then when it gets basic, it turns purple. And there's a bunch of colored compounds in there. So it's an instant, easy acid indicator. And you can do little titrations. So one time I taught the non-majors chemistry class in the summertime. It was when we were switching from Farrington to this building, and we had no labs. Farrington labs were being renovated. This building wasn't open yet. We had no labs. So how do you teach a summer chemistry course with no labs? So it was non-majors, so the department let me teach it online. So we did titrations at home in your kitchen with cabbage juice as the indicator, and I had them just take vinegar, which is 5% acetic acid, as their primary standard. So we just take the bottle concentration, 5% vinegar. They calculated the molarity, stoichiometry calculation. That was good. So I'm teaching these non-majors. Man, this is a rigorous course. They turn 5% vinegar into molarity. And then they use their primary acid standard to standardize their ammonia solution. So that's their strong base. So they went and bought ammonia. And again, told them, wear your gloves, wear your glasses. This is a real strong base. So then they titrated with drops and the indicator solution, some ammonia with the vinegar, until they saw a color change, and they wrote down how many drops. And we just took as a standard, like a NIST standard, that 20 drops is 1 mil. It's pretty close, but there's your conversion factor. 15 drops, okay? Divide by 20. That's how many milliliters you put in. Now the molarity of the acetic acid, the 1-to-1 reaction with ammonia, hydroxide, and then they get a concentration of your ammonia. Now you have a strong base. Then you go through and titrate everything in the house. Lemon juice, Coca-Cola, Sprite, wine, whatever. You titrate all of these things with your strong ammonia and look for those color changes with the red cabbage. So you can do all of that all at your house, and using these natural coloring compounds that are pH active. And so also you can do the carotenoids. and lycopene and all of these different things. These are the oranges and reds. Okay. Um, it's not that floppy because of the double bonds. This one will work. It's just really big. Okay. And then I would shy away from the chlorophylls because they have this porphyrin ring, and you got to put a metal in there. D orbitals. Okay.
So does that also mean something like hemoglobin? Would
Yes.
that be,
Yeah. Yeah. Not be preferable, yeah. If you took off the floppy parts, you'd probably get by with it. So like take off all of these extra pieces, cut all that off, and see what color you get, okay? But again, you won't have a standard, because if you're cutting off those bits and those bits actually contribute to the color, they may or may not, I just don't know. And so, I mean, that could be your research question, you know, you take that iron, different oxidation states of iron, what color do you get? You know, because that's what, from blue to red,
right,
it's oxygenated iron or not. And so if you put an iron 2 in there or an iron 3, maybe you get two different colors. But then you'll be doing two molecules. But if you get rid of all the floppy bits, it will optimize pretty easily. But we're still dealing with d orbitals, and typically we need bigger basis sets for those, and so the optimization will take longer. Yeah, and I don't know how well Zendo does with metals. So, you know, it's curious. It's a great question, but I don't know if it would be something time-wise that would just bury you. Here's a little closer look to some of those molecules. Looks like some of the chlorophylls. I don't know much about biochemistry. This is showing a magnesium atom in there. How many different atoms do we have in nature inside the porphyrin ring? Do y'all know, you biochemists? I know iron goes in there, obviously magnesium, but do you know? I don't know, so I guess we're all ignorant on that. And then indigos, we have these different kinds of purine type rings. So those are cool. So here's just some examples from the forensic course. For amphetamine, you put it through this Marquis reagent or Marquis reagent, and then it attacks this spot on the amphetamine molecule, and this makes a diarylmethine. And so you could do this one if you're forensics interested. You could do this diarylmethine. But I really don't like it because I don't like this floppy group here. So that floppy group's going to give you headaches. So I would sort of argue against that one. Here's the Lieberman test for phenols and amines, and it produces these two. One is red, one is blue. Again, they're pH active, and so this one would be good because it's really not that floppy. Yeah, you have a dihedral here, but this pi system is going to extend across that, and it's probably going to make it a little more rigid. So you could check this one out. If you do this one, go ahead and do both. It's not going to take that much longer, and you can see if you get the red and the blue color for those two molecules. Here's the marijuana. Again, this one's going to be super floppy with THC. These THC compounds take forever to optimize. But this azo linkage, this fast blue has this azide, and it'll attack the molecule, and this is something too. These lazy people, it could attack here or here, and so they just say they stick it to the ring, like it's not bonded to the middle of the ring, right? They're just saying it's going to be in both positions, and so we don't care which one. We're just going to capture both by drawing the arrow to the middle of the ring. But that throws students sometimes. So they're like, how does that bonding work? It's showing the bonding to something that's nothing, you know, there's the middle of the ring. So now what level of theory should I use? This is a student's work here years ago, Nathan Baker. He wanted to do a research project during the semester, and I said, okay, I want you to model the color of this nitroaniline, these three nitroanilines, at like 5 or 6 different levels of theory, and do Zendo and time-dependent DFT and configuration interaction with singlets, excitation. And so these are the colors that came from Zendo all the way down, based on basis set. And these are the colors that came from time-dependent DFT, and these are the colors that came from CIS, the configuration interaction. You see, the CIS really didn't give much strong color. The Zendo was the strongest color, and I found that there were options that gave pretty good results for the Zendo. So this was how we decided on the basis set, was deciding that optimizing at 6-31G DP, let's see, this is the only one that doesn't really come in very well. Look how brown this looks, and yet it's predicted to be yellow. Remember I talked about saturation when something's really concentrated. And here we have crystalline molecules. It's 100% concentration. And so it is yellow at dilute solutions, but there's so many molecules in the crystal that it looks like a dark brown. And it's because it's absorbing all of the wavelengths of light. It's saturated and it's tailing out, and all you get is sort of a brown light coming through. This is definitely what happens with permanganate. Very strong absorber. If you look at permanganate crystals, they look black because they're so concentrated. It's 100% concentration. You put one crystal of that in water and you get this beautiful pink purple color. Yeah. So sometimes looking at the solids, you cannot tell what color it is. You put a little drop of that in, or a little powder of that into solution. Now it's dilute, and you get the molecular color. Okay. And so here's the procedure for your task 2. And we're just going to have 2 tasks. Task 1 is the color card and the experimental spectra, turning those into RGB values, taking that picture and using ImageJ to kind of get the RGB values of those and seeing how well you did. Okay, that was task 1, and that's been published out there already for you guys to put together. Now this is task 2. This is the simulation side of that. So everybody build azulene and whatever molecule you've chosen in Gauss View. So we're going to do minimum of 2 molecules. Yeah, minimum. If you wanted to do like this one here, you would do 3, right? You would do azulene and then these 2, the red and the yellow version. Okay, if you were excited about it. Okay. Do an op freak. I'm going to go ahead. We just pointed out that there was this basis set is screwed up. 632. That's nothing. So let me just rewrite this, and it's 6-31G, and let's do a D and a P. It'll take a little longer by putting those p orbitals on the hydrogens, but that was the thing that we determined here, was this was the 631G DP was the better one. So that's the geometry optimization step. And then what I mean by iterate is you look at the frequency output. If there's imaginary frequencies, try to figure out how to change the geometry to get to the minimum. So let's say you have a methyl group stuck on a ring or whatever, and you animate that imaginary frequency, and it's the methyl group turning. It's telling you turn that dihedral a little bit and resubmit the job. So you animate the dihedral, you animate the imaginary frequency, and it will tell you what motion that you need to tweak. Okay, so go in and, like for the methyl group, pick the dihedral angle and change it a little bit, and then resubmit the job, and it'll find the global minimum there. If that's your imaginary frequency. So that's what 3 means. Iterate until there's no imaginary frequencies. This is why we want a more rigid molecule. If you had that fast blue whatever with all those dihedrals, you might have 6 or 7 imaginary frequencies. You're going to have to go in and find the combination of those. So it could be, let's just say it was 2 combinations of 6 variables. That's 2 to the 6th power. Okay, that's a lot. So you have that many combinations, and so you don't want to do that. Okay, then once you're finished with the optimization and the frequency job, open the log file to carry that optimized geometry into the Zendo calculation. So when you open the log file, you've got the optimized geometry. Go up to calculate and set up the Zendo job. There's a video on that, and we can do it here in a second. So you set up the Zendo calculation, and then you want to run it for singlets and 20 states. This is going to be, like I said last time, enough for the smaller molecules. If you finish your Zendo calculation and you pull it up and you go down to the 20th transition and you're still producing transition wavelengths that are greater than 300, then you need to add more states. Okay, so we want we want all transitions. We want, let me just draw this here. Wavelengths greater than 300. So you should see your list of wavelengths, it might be like 520 and then 402 and 306 and then 277. And so you can just cut it right here, okay, when you do your modeling, okay? But what if you got a molecule and it's 708, 655, 5 something, 512, 416, and 4116. And then it keeps going, and your 20th state is like 386. We're not past 300 yet. And so we need more states. So you need to redo the Zendo job and do end states equals 30, end states equals 40, sometimes 60 is needed. And then you'll get 60 transition wavelengths. And then you'll put those into the color tool. I don't think y'all's molecules are going to be big enough to have to worry about that, but that's what you would do. If you're trying to model the visible spectrum, you need all of the peaks that might contribute to the visible region of the spectrum. Okay. And then you copy those transition wavelengths and oscillator strengths into the colorimetry tool. Best way to do that, I think, is just to copy that whole section and paste it into Excel. And then do text to columns. And so then one of those columns is going to have your wavelength in it. Select all of that and sort by wavelength. So all your wavelengths will pop up to the top, and you can delete all that other trash. And so it's a way to sort of consolidate all of those lines that have the wavelengths in them. I'll show you the output file here in a second. And then explore what peak widths and asymmetry parameters produce the best color match. And so since you know you're doing a known color match for the azulene, and then for your molecule you should have that reference color, then you can determine which asymmetry parameters and peak widths. And it may be that you can't get there from here, that your peak is in the location that no matter what width you choose and no matter what asymmetry you choose, you can't get the right color. And that's okay. It's just inaccurate. Okay? But you got to at least try. See if you can find a combination of peak width and asymmetry that gives you the color that you have as your known. Okay, and so that's going to be down here your discussion on the difficulties you had and on whether it was accurate or not. So this is the following the task 2 items that you're going to add to your PowerPoint. So task 1, you're going to have some items for the PowerPoint, then you're going to add these to the PowerPoint. Molecular structures, screenshots of the colorimetry tool, and so on. So let's look at this colorimetry tool. I'm going to put this up on Blackboard today so you'll have access to it. Come on, Excel. Here it comes. Okay. And change this to Excel. Okay, we're going to have to do this. Yeah. All right. Okay, so here's the color analysis tool. So here's you put in your wavelengths. Let me make this intensity 0 for the 350 peak just for now. And I'll show you that 550 thing that we had. So here's our peak at 550, and you can do update colors, and you see that nice blue color. What if I had the asymmetry parameter of 2? I get a deeper blue. Remember I did that one at 0.5, so it tails the other way. Update the color. I get red. Okay, same peak location. So you have a very important parameter is that asymmetry parameter. Here's the data import. So this is the output that you get from a Zendo calculation. Let me show you the actual log file. Let's see. Where do you see G16? Here it is, scratch. Okay. And here's my phenylethylamine. So here's the log file. Scroll down until you get to this region right here. See, excitation energies and oscillator strengths. These are the transitions. And you see this wavelength, that's the transition wavelength. And here's the intensity, the oscillator strength. So that's the solution to the transition dipole moment integral. So we select this whole region. And this isn't a great one because it's 100 and something nanometers, so it's not even visible, okay? We go down here, and you'll go down until you get to 300, and you don't need to pull any ones that are less than 300. Mine starts right here at 187. Let me just pull the first 4 along. So I'm going to grab that. I'm going to go back over to my Excel file, and just delete all of this mess, and I'm going to paste it here. Control V, and see there it is, but it's all in text. So I need to do data, text to columns, and I could pick fixed width. I could do lots of things. Let's do fixed width, and I really don't need all of these. You can double click all of these guys and get rid of them. But I want to keep that one because that's going to be the column where my wavelengths are. See them all? And then I'm going to put one right by that F equals. I can get rid of this one because that's my intensities. You see them? Hit next. I could go through and I could like not import this one and not import this one and not import that one. And hit finish. There's my wavelengths and my intensities. So if I just come along here and I sort, hello, yeah, there they are together. And I can copy those and I can paste them right here into the main page. Now I don't want to do that because this is all in the UV. It's 140 nanometers. So, but you know, yours. If your peaks are all shorter than 300, there's something wrong. It's not colored. You got a UV active molecule that's not colored. There's nothing in the visible. Okay, so right there you know something's wrong. There's no peaks in the 400 to 700 nanometer region. That's a problem. You've got a colored molecule and you're predicting that it only has UV transitions. That. So hopefully that doesn't happen to you. If that happens to you, text me. I was like, what'd you do with your molecule? Did you build it right? You know. Now these are all of the different things that you know about. This is the convolution. This is the generating the absorbance spectrum. Here's the absorbance spectrum at different concentrations. Here's the conversion into transmittance. Here's the colorimetry. Here's the different observer functions. So all of these pieces that you know from task 1 are collected in this main page. And it has this macro that lets you. Now the concentration, sometimes maybe it's not very strongly colored, and so you can go up by 2 and it'll get more darkly colored. You can go up by 3 and now everything's tripled and it gets even more darkly colored. Let's do 10. Okay. It's getting darker. Okay. Sometimes you can get it to totally saturate. Let's do 1.1 on this. Yeah, see, it turns black. Like it's so concentrated, it turns black. Kind of a black green, yeah. And look how fast the chromaticity diagram gets off of the white spot. It goes light blue, dark blue, black. Okay. If If you could also do 10 to the first power, 1 times 10 to the first power, and that's the same thing. Okay, so that's what the 10 to the thing here is. In case you wanted to multiply by 10 or 100 or whatever, if you have really, really small oscillator strengths. Okay, but anyway, we can do 0 here, and we can do 2 here by default, or 1.5, and then we get a nice progression of colors. Yeah. So that's your tool that you'll use to do the colors. Hopefully you understand what's in the tool. You've got the convolution of each of those peaks with a Gaussian, or not, actually not a Gaussian, a log normal peak. And then you've got the concentration and absorbance, and then the conversion to transmission. Okay. I think it's going to be great. And we'll have some, Friday we won't have class, so y'all work on your projects, read those papers if you want. And then Monday we'll have time for questions. So do not wait to start the project next week. Start it this week. Try to get as far along as possible. Questions on task 1 or 2 on Monday. Okay, I don't have a lecture for Monday. You got to bring your questions.